Hi, everybody. Here is another video solution. This is section 6.2, exercise 7. It says, let beta be a basis for a subspace W of an inner product space V, and let Z be a vector in V. Prove that Z is in the orthogonal complement of W, that's this W perp thing, if and only if the inner product of Z and V is equal to 0 for every V in beta. All right, so as this is an if and only if proof, let's prove both directions. So first, we will show that if Z is in the orthogonal complement of W, then the inner product of Z and V is 0 for every V in beta, and this will be a pretty straightforward proof. Suppose that Z is in W perp. Well, what it means to be in the orthogonal complement of W is that you are orthogonal to all of the things in W. So in particular, you should be orthogonal to all the vectors in a basis for W. So let's just write that out. By definition of W perp, for any vector W in W, capital W, the inner product of Z with W is equal to 0. Thus, in particular, for each V in beta, well, being a basis for W means that you are also in W. So for each vector beta, V in beta, V is in W. So the inner product of Z with that V is also 0. Great. So that's one of the directions. Done. So the real content of this problem is in the converse, the reverse direction. Right now, what we want to do is suppose that the inner product of Z with V is equal to 0 for every vector in the basis. And now we want to show that the inner product is also 0 for any vector in W, right? That you're actually in W perp. So you have to be perpendicular to all of the vectors W from capital W, right? So suppose that Z inner product with V is equal to 0 for all the vectors V in beta. Then we want to show that for any vector W in the subspace W, the inner product of Z with that W is equal to 0. So how do we do that? Well, we need to show this for all W and W, so we take an arbitrary vector from them. Suppose little w is an arbitrary vector in W. Well, since beta is a basis, it spans capital W, so we can write any vector from W as a linear combination of the vectors from beta. That is true in particular then of this arbitrary vector W. So since beta is a basis for W, there exist, I'll now label them, say, V1 through VK in beta, and I'll say A1 through AK in the field, so that W is that linear combination, I equals 1 up to K of AI VI for those basis elements of V sub I. then, well, what happens now when we take the inner product of Z with W? Well, since W is this linear combination, we can replace W with that expression. And now we can use the properties of an inner product to break up this sum. That is, we get, oops, we could pull out the sum, because even though the definition of an inner product only says that the inner product is linear in entry, it does in fact respect addition in the second entry as well, which we showed in class. All right, so that is the sum now of the inner products, of Z, just one Z, not Z sub I, of Z with AI VI, and then also by the sort of conjugate linearity. I can't pull out the AIs for free, but I can pull them out by putting a complex conjugate on them. So the inner product of Z with W is equal to a sum of the complex conjugate of the scalars times the inner product of Z with each of these VI, but now by the supposition, Z inner product with any vector from beta is equal to 0. So each of these pieces right here is 0. So even though there are coefficients there that are complex conjugated, it doesn't matter. This is a sum of zeros and therefore is 0. So what we've really shown now is that for any vector in W, the inner product of Z with W is 0, since that vector W is just a linear combination of the basis elements. Hopefully that was helpful, and I will see you guys later.